In this session today, we'll discuss how the custom labels feature in Amazon Rekognition service can be applied to a real-world use case. My name is Raju Pinmetcha, and I work as a specialist AI/ML Senior Solutions Architect at AWS. Our agenda for this session is as follows. We will discuss what the customer problem is, how we figured that Rekognition custom labels can address this problem, how the solution is being implemented with the customer right now, and we will end this presentation with some lessons learned in the process. Problem that is of interest to this customer is how farmers can recognize weed in their crops in an automated manner. Today, farmers locate their weed in their fields through visual inspection and sometimes through in-field cameras. That is a manual and time-consuming process. Before discussing an AI-based solution, let's first discuss what decisions a business needs to make when they face a challenge like this. For a computer vision problem, what comes to our mind is Amazon Rekognition. Amazon Rekognition standard service is good with recognizing faces, detecting objects, scenes, and so on. However, it's not built to answer a computer vision classification problem as we see in these two images. Now, one option that our customers have in a situation like this is to hire a data scientist and build a deep learning model from scratch, but that is time consuming and expensive. That is where Rekognition custom labels come in, as they are built to handle these kind of problems. Normally, solving a computer vision problem using deep learning requires thousands of images, if not more. However, in the case of Rekognition custom labels, we were able to build a good model using only 32 images. Here I am on the Rekognition custom labels console, and if I click on this project called weed detection in crops, and let's click on the training data set, we will notice that there are 32 images that I had used, out of which are 16 images that have good crops in them. As you can see here, there's no weed in them. And I also have 16 other images that have weed in those images. So after completing the training of the model, we got some results. So let's look at that. So if I click on the model, we will see that we have a near perfect model in this case. It has a F1 score of 1, precision of 1, and a recall of 1. What I also did was I uploaded 4 images as my test data set. This is the data that my training model had never seen. So let's look at the test results. Here we see 2 images of good crops, and it had correctly predicted that these crops are indeed good with a confidence of more than 90%. If I scroll down a bit, we will see that I had 2 test images that had weed in them, and for this also the model had correctly predicted that there is weed in them. We have a cloud formation template at this GitHub location that one can run in order to test this model from a browser. All relevant details are available in here. You can click on any of these links here. Depending on which AWS region your account is in, it will then spin up the required resources to give you a front end. Here is that front end. Now make sure that this model is running, and if I click in here, it will let me upload a test image so that I can make a prediction in real time. In this case, it had predicted with 92% confidence that there is weed in this image. You can also run this through the SDK. Documentation for the SDK is available at this location. This is the code, and if I run it, it's going to show me again similar results as we saw in the browser, that the model is 92% confident that there is weed in this image. At present, researchers of this customer are working with us to start implementing the solution so that farmers can feed frames from their field cameras, drone videos, and so on directly into this algorithm and automatically figure which areas of their crop require treatment. So this can potentially save hours of manual efforts for these farmers today. In addition, this technique can sometimes be more accurate than what a human eye can detect, making it an effective solution both on accuracy and cost fronts. We have some lessons learned in this process that we want to share with you. Try building models with recognition custom labels in an iterative manner, although that is not a requirement. For example, if the model results are not great, see if you need to improve your image resolution. You can also feed more images or crop any unwanted noise from the image background to further improve your model accuracy. Thank you for your time today.